Okay, welcome to part 2 of our Unit 13 discussion of acids and bases. The same objectives that we looked at for the first video are still in effect, so I'm not going to bother reading those. We're going to jump right in and talk about some acid-base definitions today. When you think about an acid especially, not so much with a base for some reason, but when you think about an acid, your brain definitely takes on certain pictures. But it's really helpful for us in chemistry to define what an acid and a base actually are. And that definition has changed through the years the more that we have understood acids and bases. We're going to be examining two definitions today. The first one is the Arrhenius definition of acids and bases. Svante Arrhenius was a Swedish gentleman who said that an acid was any substance that when you put it in water, it would give up hydrogen ions. We know now that hydrogen ions, whenever they're in water, they will react with the water molecule to actually add a third hydrogen on there and turn it into what's called a hydronium ion. But for all intents and purposes, you can use hydronium and hydrogen ion pretty much interchangeably. You can see right here in the picture, you've got hydrogen chloride or hydrochloric acid. When it comes in contact with water, this hydrogen comes off of the chloride ion, attaches itself to the oxygen that's already hooked up to the two hydrogens, and you get this hydronium right here. You also get a negative chloride ion. And it's this hydronium that makes an acid an acid. Arrhenius also said well, I think actually that's basically everything I just said, so moving on here. And there he is, there's the man. He said that a base, on the other hand, was anything that whenever you put it in water, it gives off hydroxide ions. This one's a little easier to spot. Most of the time, when you've got a substance that has hydroxide in the name, you can be pretty sure it's going to be a base. Something like sodium hydroxide, which is Li, potassium hydroxide, barium hydroxide, and so on. You keep seeing this OH ion show up in there. When you put those in water, of course, they're going to dissociate. They're going to give off that OH, and that OH is going to be what makes a base a base. If you take a look here, you've got NH3. Now, NH3 is ammonia. Ammonia is a base. It doesn't have an OH on it, though. So you have to wonder, okay, where is that OH coming from? Well, if you take a look at what happens in the picture here, the ammonia is actually going to be stealing another hydrogen from water when you put it in there, which makes ammonium ion. And in the process of ripping that hydrogen off of the water, you get that hydroxide ion. Another definition we look at is by two different gentlemen whose last names were Bronsted and Lowry. I always forget their first names because they're nowhere near as much fun as Svante. But they basically said that acids are proton donors. Now, a proton is a hydrogen ion, so you might be thinking, well, is it the same thing? You're just calling this a proton, and Arrhenius called it a hydrogen ion? Not really, because they also said that a base is anything that accepts a proton. Okay? So acids donate protons, bases accept protons. So in order for you to have a substance be an acid, it has to give away a proton, but it also has to have something there to take that proton up. So anytime, according to Bronsted and Lowry, that you have an acid, you must also have a base. And so if you look here in this reaction, we've got hydrochloric acid, okay, which you guys should all be familiar with by now. But if you're looking around for the base, there's not a base just readily there. There's nothing with hydroxide in it. But if you take another look, what's going to happen when we put that HCl into that water? That water is going to take that hydrogen ion. It's going to take that proton, and it's going to become hydronium. And so we say that HCl is the acid, H2O is the base. Now look and see what we have left over. After chlorine gave away that proton, it's now a negative chloride ion, which means that it could take on a proton from somewhere else. So it could act as a base, and we say that chloride is what's called the conjugate base of hydrochloric acid. Furthermore, down here we've got this hydronium ion. It just took on that extra proton. Well, it could give it away again. And if it gives away a proton, that would make it an acid. So we say that hydronium is the conjugate acid of water. And I know that's a little bit confusing because you don't normally think of water being an acid or being a base. But really, it's a lot simpler, so don't let your brain get in the way too much. If it gives away a hydrogen, it's an acid. If it takes a hydrogen on, it's a base. That's really all you need to worry about for the Bronsted-Lowry definition. And there are Mr. Bronsted and Lowry. Don't ask me which one's which. They probably don't care whether you know or not anyway, so let's move on. I said this just a moment ago. I'm not going to bother rereading it to you, but conjugate base is what you have left over after an acid gives away a proton. And a conjugate acid is what gets made after the original base takes on that proton. I am not entirely sure why we're re-mentioning this here. Don't forget indicators. Oh, I know why. Indicators, the way that they work, the way that they change color, is by either taking on or giving off some of those protons. They're very, very weak acids or bases that interact when acids or bases are present. And as they're taking those protons on or giving them off, they do change color. Something about the molecule itself, the way that it reflects or absorbs color, changes. So according to this, looking at this reaction, this is a Bronsted-Lowry acid-base reaction. Who up here is going to be my acid and who up here is going to be my base? You have to look and see, where's the hydrogen? Where is it going to be coming from? Well, both of these guys have hydrogen, right? But look and see what happens after the reaction's over. Water, he started with 2, now he's got 3. So the hydrogen came to him, which means that water here is going to be our base. HNO3, this is nitric acid. I guess that kind of gives it away. Notice that whenever the reaction's over, it doesn't have that hydrogen ion anymore. It's just nitrate ion. And so HNO3 here is going to be our acid. And you can see down here, here's water, here's nitric acid. So you have your base, you have your acid. Now, if this is your base, if water is your base, what does that make hydronium here? Come on, say it out loud. You know I can hear you. What? Yeah, you're right. Yes, this is the conjugate acid. Very good. Which would then make nitrate. Yeah, you got it. That's right. It's your conjugate base. So if you take a look here, just a couple more examples here. We've got hydrofluoric acid, and water here is acting as our base because it's going to be taking on that hydrogen from the HF, leaving fluoride ion behind as the conjugate base, leaving hydronium as the conjugate acid. Now look here. Here, ammonia, NH3, is the base. And, well, wait a minute, wait. Now water is an acid? Yeah. Because look, water was a base in this reaction when it reacted with an acid, but here it's reacting with a base, so it's going to be giving that base one of its hydrogens. And so what's left over from water is that hydroxide ion. So here's the thing. Water can act as both a base and an acid. Okay? The word for that, we say that it's amphoteric. Now you've seen this ampho, A-M-P-H, root before. Think amphibian. Okay? That means double life. Amphoteric means that it can act kind of as a double agent. It can either be an acid or a base. I mentioned this just a moment ago. Lots of other substances can also be amphoteric. So just to kind of sum things up again, we have Mr. Arrhenius who said that An acid is a hydrogen ion producer, and a base is a hydroxide ion producer. And you had Misters Bronsted and Lowry, which said that an acid was a proton donor and bases are proton acceptors. So for the most part, they're pretty much saying the same thing. It's just using a little bit different language. And there is a third acid-base definition called the Lewis acid-base definition, but we're not going to be worrying about that this year in Chem 1. And that's the end of the video. Thanks for watching.